So today we're going to talk about constrained motion. So constrained motion, basically it just has to do with objects that are connected. That means that the motion of one constrains the motion of the other. A simple example of this is the example of pulleys, which are used to change the direction of motion of a system. So we'll be working with ideal pulleys in this situation. Um, this means that the pulley is massless and frictionless, and it changes the direction of tension without affecting the magnitude of that tension. So first we'll look at a system with two particles connected by one rope. So we can assume in constrained motion that the rope is inextensible, and we want to focus on a fixed length portion of the cord. So first we're going to define a coordinate system for the system of particles relative to a datum, which is just a fixed reference point. And you can choose this to be wherever is suitable, which we'll see in a bit. And then we want to create an equation which relates the two particles to the cord length. So then to simplify, we can disregard any portion of the cord which maintains a constant length during motion. Then we want to differentiate the position equations to obtain velocity and acceleration equations. This is only if you're asked for it, of course. Finally, we want to make sure at the end that we've maintained a consistent sign convention. Just as a general convention, positive is where a particle moves away from the fixed datum. With multiple ropes, it's pretty similar. All we have to do is examine the problem and the problem diagram to determine the number of ropes relevant to the motion, write a length equation for each rope, and the motion of each rope must be related to the motion of the other ropes. And this will be possible to do with multiple ropes, unless, of course, those ropes aren't connected, in which case the systems are separate, and it wouldn't be possible to, well, the systems don't affect each other, essentially. So just go over an example. So we have here a block, which is A, and we want to determine the velocity of it if the acceleration which is happening at C is equal to 0.9 t, where t is the time in seconds. And then there's also this extra example here which deals with more than one rope. But we'll do this one for now. So I already have the diagram here. So I'm just going to draw this in terms of a datum and sort of reference point. So I'm just going to redraw it quickly here. So it looks something like that. This going down. And just a note that this rope here does not affect this pulley here. Okay, so now what we want to do is define a datum, which an easy one to do would be just this one here. We don't need to account for this portion of rope because it never changes during the motion, but the rest of them, the length would change. So then we can set up our system here. Again, we don't need to account for this length of rope because it doesn't change during the motion. So I'm going to call this SA. So that's length A, which goes from the datum to A. And then we just need one more. And we're going to call this SC. So we have the diagram in terms of SA and SC, and that's really all we need because that will account for all of the lengths of rope. So I'm going to move this down, and we want to find, so the length of the rope, the length is equal to, and I'm just going to go up here so we can show it. So if we start from, say, hang on, change it. If we start from, say, here, and then we go up the rope, that would be SA. And then we follow the rope. We don't have to account for it over the pulley. Again, that length doesn't change. So then that would be SA again. And then this portion of the rope here is SA plus SC. So hopefully you guys can see that. So we can just, in total, the rope length would be SA plus SA plus SA plus SC. So we'll say that SA plus SA plus SA plus SC. And this, of course, is equal to 3SA plus SC. So that's the length of the rope. And then from this length equation, we can differentiate to find the velocity equation. So that would be 0 because the length is constant. So length is 0. And then we would simply differentiate SA. So that would be 3VA plus VC. And that's our velocity. And then we can do it one more time for acceleration. Let's write down velocity and acceleration. Differentiate one more time. And we'll say, so this is 3AA plus AC. Okay. So we know AC. That is given to us. So what we want to do then is we want to find VA. So that's what we're looking for. But in order to do that, we need to use this acceleration equation here. Because we know the acceleration, actually I'll say, so we need to find this, and we know this. So we want to use the acceleration of C to find the velocity of A. So we can do this by isolating for the acceleration of A. So, of course, just basic algebra, acceleration of A is equal to negative AC over 3. And we know that AC is equal to, let's see, what is it here? 0.9t. So negative 0.9t over 3, which, of course, is equal to negative 0.3t. So then we want VA. So I'm just going to write this out one more time. So if we want VA, we have to take the integral of this. So I'll do that now. So from 0 to VA, dVA equals, and then take the constant out, negative 0.3, and then t and 0 are limits of integration, and after we take the constant out, it's just t. So then we can write this out, and we can say that, okay, VA, that's what this would be. So it would be VA minus 0, I guess, if we want to be technical about it, equals negative 0.3, and then t squared minus 0. So then VA equals, oh, sorry, I missed one step here. That'd be over 2. Yeah, because it, yeah, okay, that was my bad. It'd be all over 2. So just make more room. So then VA would be equal to negative 0.3 t squared over 2. And this can simplify just to be negative 0.15 t squared. And then we want VA at 4 seconds. So VA equals, and then we just replace t with 4. And this would be equal to negative 0.15 times 16. And of course you can do that, the math there. I just don't have a calculator handy at the moment. But that is how we get from knowing just the acceleration of c and the time to knowing the velocity of a. All right, that's everything for today. Thank you again to Loom and Google Keep, and as well as to my professors who taught me this. And I hope to see you again next time.